SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will start with preliminaries of turbulent flow and heat transfer. Now, let me make some introductory comments on turbulent flows. The following are the characteristics features of turbulent motion. One is irregularity. Complex variations of velocity, temperature, etc. with space and time are the dominant properties of a turbulent flow. The irregular motion is generated due to random fluctuations. It is postulated that the fluctuations inherently come from disturbances such as roughness of the solid surface. They may be either damped out due to viscous damping or may grow by drawing energy from the free stream. As a Reynolds number less than critical, the kinetic energy of flow is not sufficient to sustain the random fluctuations against the viscous damping. So at a Reynolds number less than critical, the kinetic energy of flow is not enough to sustain the random fluctuations against the viscous damping, and in such cases laminar flow continues to exist. At somewhat higher Reynolds number than the critical Reynolds number, the kinetic energy of flow supports the growth of fluctuations and transition to turbulence is induced. Now, strong mixing is another feature. Heat transfer of or momentum transfer. So these are enhanced due to this strong mixing. So high transfer of momentum, heat, mass by fluctuating turbulent motion. Practically this is the most important feature. Turbulent motion is always 3D. For a parallel flow, usually in laminar parallel flow, one component of velocity is non-trivial, other components are trivial. In a similar parallel flow situation, if we consider that the velocity in the mainstream direction is mean plus fluctuations, and y is the normal direction to the flow. Uppercase gamma is any space variable. Fluctuations are expected to be in the space. Even if the bulk motion is parallel, the fluctuation u prime being random varies in all directions. Now let us look at the continuity equation. So if we substitute u by u bar plus u prime, we can write in this way: del u bar del x plus del u prime del x plus del u del y plus del v del z equal to 0. But del u prime del x is not equal to 0. The above equation depicts that y and z components of velocity exist even for the parallel flow if the flow is turbulent. That means u is u bar plus the fluctuation in u. Even though there is no mean velocity in cross stream directions, in y direction or z direction, mean velocity we can write as 0, but there will be fluctuating components in order to satisfy the continuity equation. So that means if there is fluctuation in any direction, ideally any component of motion, it will induce fluctuations in all other directions or all other components of motion. Turbulent motion carries vorticity, and vorticity is composed of eddies interacting with each other. We can look at this picture. This is a free jet emanating from a nozzle, and if we place sensors at different locations at the same x distance from the outlet of the nozzle, we will be able to see the fluctuations at every locations, and these fluctuations are such that they have no similarity if we look into signals at these 6 points. At any t, they are not similar, and they are also arbitrary at any instant for any particular signal. So turbulent motion carries vorticity and consists of interacting eddies. Wide spectrum of eddy sizes and corresponding fluctuation frequencies are shown here. In a turbulent flow, energy is fed from large scale mainly to smaller scales by nonlinear processes. The term homogeneous turbulence implies that velocity fluctuations in the system are random. The average turbulent characteristics are independent of the position of the fluid, that is invariant to axis translation. If the velocity fluctuations are independent of axis of reference, that is invariant to axis rotation and reflection, this condition leads to isotropic turbulence, which by definition is always homogeneous. Now, we will not take up various other issues about the turbulence physics. We will take a route to the classical idealization of turbulent flows, so that turbulent flow situations can be handled with good degree of accuracy also. Now, usually for this, we go for statistical calculation methods. where details of turbulent fluctuations usually are not considered. Hence, the statistical approach is taken and turbulence is averaged out. Different trends of variation of the mean and fluctuating components will show in a figure in the next slide, where we can consider all the velocity components as the summation of mean and fluctuations, pressure as mean pressure and fluctuating pressure, and this mean is basically time mean component over a time interval. So here we have shown that a steady mean motion, that means the instantaneous velocity can be decomposed into mean component and fluctuating component. Now, fluctuating components are such that if we perform the mean signal or the mean component, then the mean is not varying with time. So over a large time scale, we can see mean is steady. But if we reduce the time scale, then we can observe or we can appreciate the fluctuations. Similarly, this mean motion can also be unsteady mean motion. Here we can see the fluctuating components are there, but when we perform the average velocity, we try to determine the average velocity and observe the variation of average velocity, we will see the average velocity is also changing with time. And this variation has a different time period, which is much larger than the turbulent fluctuations or than the turbulence time scale. So here the time period is very small for the fluctuating components, so frequency is high. Here the time period is large and variation of this frequency is much less. Now, the fluctuating components do not bring about the bulk displacement of a fluid element. The instantaneous displacement is u prime dt, and if that is indeed not responsible for the bulk motion, then we can write this integral T naught to T naught plus delta t, the time window, u fluctuation dt, this has to be 0. There is no bulk motion and these are all instantaneous displacement. Due to the interaction of fluctuating components, macroscopic momentum transport takes place. Therefore, interaction effect between two fluctuating components over long period is non-zero. So, between two fluctuating components like u prime v prime, this, if we perform the integral over a time window, dt is non-zero. We take time average of these two integrals, that means this integral and this integral, then u prime bar, that is average of u prime, that is 0. Since this integral is 0, so u prime bar is 0. And u prime v prime bar, since u prime v prime dt, this integral is non-zero, so u prime v prime bar, this is non-zero. So u prime bar is 0, but the quadratic quantities, that means u prime v prime, u prime w prime, u prime bar, those are non-zero. Now we can make a general statement with any two fluctuating parameters, say f prime and g prime. And those f prime and g prime can be vectors or passive scalars. So they can be fluctuations in velocities or fluctuations in temperature. Now f prime bar equal to g prime bar equal to 0. Similarly, dds of f prime bar equal to d2 ds2 f prime over bar, that is also equal to 0. But f prime g prime over bar is non-zero, and dds of f prime g prime over bar is also non-zero. So we shall state some rules of operating on mean time averages. If f and g are two dependent variables and s denotes any one of the independent variables, x, y, z or t, we can write basically df ds over bar equal to dds of f bar, or integral of f ds over bar is integral of f bar ds. So with this philosophy, this is called Reynolds decomposition, that is instantaneous quantities expressed in terms of average and fluctuation. So u equal to u bar plus u prime, v equal to v bar plus v prime, w equal to w bar plus w prime, p equal to p bar plus p prime. If we plug in this into continuity equation and do little algebraic operations, we will get two results. One is divergence of ui bar equal to 0. That means del x of u bar plus del y of v bar plus del z of w bar equal to 0. And divergence of ui prime is 0. That means del x of u prime plus del y of v prime plus del z of w prime equal to 0. Now we can write x momentum equation in conservative form and apply this Reynolds decomposition and then average out the entire equation to see the time averaged equation for x momentum. So the basically as I said, that conservative form of equation, rho del u del t plus del x of u square plus del y of uv plus del z of uw. This is the left hand side. You can easily see that if we find out the derivatives and then apply the continuity equation, we will get del u del t plus u del u del x plus v del u del y plus w del u del z. That is usually referred to as non-conservative form, and we can just rewrite the same equation retaining everything intact in conservative form, equal to minus del p del x plus mu del 2u del x2 del 2u del y2 del 2u del z2. And then as we decided, we'll apply Reynolds decomposition. That means del t u plus u prime. U is this will be u bar plus u prime. U mean plus u prime over bar. Then we will get del t of u bar plus del t of u prime over bar. There is a small mistake. This u is mean component. U bar should have been u bar. There is a typographical error. Consider this as u bar. U bar plus u prime over bar. That will produce del t of u bar plus del t of u prime over bar. So del t of u prime bar, we have seen that is 0. So this is del t of u bar. So from this term, after averaging out, we get del u bar del t. Similarly, let us look at the second term, del x of u plus u prime, u bar plus u prime, in u square. So again u bar plus u prime over bar. So we can write del x of u bar into u bar plus del x of twice u bar into u prime plus del x of u prime square, entire quantity under over bar. And then as a result we will get del x of u bar into u bar plus del x of u prime square bar. U prime square bar is non-zero. So we again take up the third term or second convective term, del y of u bar plus u prime into v bar plus v prime over bar. So we can write del u bar, del y of u bar into v bar, del y of u bar into v prime, del y of v bar into u prime, and del y of u prime v prime, entire terms operated by over bar. And after applying over bar, from first term we get del y of u bar into v bar, but second and third term, second term will get del y of u bar into v prime bar. V prime bar is 0. From third term we will get del y of v bar into u prime bar, and u prime bar is 0. So they will not contribute, but u prime v prime over bar, which will produce del y of u prime v prime bar, that is non-zero, that will be there. Then we take up the third term, del z of u bar plus u prime into w bar plus w prime over bar. In the similar way, finally we will get del z of u bar into w bar plus del del z of u prime into w prime over bar. So temporal term and the convective derivatives we have found out. Now this p is p bar plus p prime, and if we apply over bar, again p prime bar will be 0. We'll get del p bar del x. We have not written it here separately, but substituting p equal to p bar plus p prime and applying over bar, we will get minus del p bar del x. And then the viscous terms, del 2u plus u prime del x2 over bar. We can see this will produce del 2 u bar del x2 plus del 2 u prime bar del x2. Now again this is a special variable but being operated on u prime bar, which is 0. So this will not finally contribute. We will get del 2 u bar del x2. Similarly, from the second term we will get del 2 u bar del y2, and from the third term we will get del 2 u bar del z2. So having found out all these values, if we plug in, we will be able to conclude that. So we can say introduction of Reynolds decomposition into the Navier-Stokes equations and subsequent averaging and application of the laws of statistics leads to the appearance of turbulence correlations, that is turbulent or Reynolds stresses. For example, from the first equation now, if I come back with the contribution of individual terms and rewrite, we will get rho del u bar del t plus del del x of u bar into u bar plus del del y of u bar into v bar plus del del z of u bar into w bar equal to del p bar del x plus mu del 2u del square u bar. That means del 2 u bar del x2, del 2 u bar del y2, del 2 u bar del z2. However, these three terms which were produced while averaging the left hand side, del del x of u prime square bar, del del y of u prime v prime bar, and del del z of u prime w prime bar, those will be there and they can be transferred to the right hand side and with the multiplier rho. Then we'll get rho del del x of u prime square bar, del del y of u prime v prime bar, and del del z of u prime w prime bar. So these three terms will act as additional stress terms with the viscous stress, and they are called components of Reynolds stress, which is basically culmination of the contribution of the fluctuating components due to Reynolds decomposition and subsequent averaging. So now again we can go back from this conservative form to non-conservative form, and we can write rho del del t of u bar rho u bar del del x of u bar, v bar del del y of u bar, and w bar del del z of u bar. Just like the laminar flow terms, only thing, all the velocity components are replaced by their average, time average quantities. Minus del p bar del x plus mu del square u bar minus rho, and then these three terms, del del x of u prime square bar, del del y of u prime v prime bar, del del z of u prime w prime bar. So this becomes time averaged x component of Navier-Stokes equations for turbulent flows. Similarly, if we apply exactly similar treatment on y momentum equation and z momentum equation, then we'll get time averaged y momentum equation, which is rho del v bar del t plus rho u bar del del x of v bar del del y of v bar, w bar del del z of v bar equal to minus del p bar del y plus mu into del square v bar, that means del 2 del x2 of v, del 2 del y2 of v bar, and del 2 del z2 of v bar, del 2 del x2 of v bar plus del 2 del y2 of v bar plus del 2 del z2 of v bar, and then the fluctuating contribution of the fluctuating components minus rho del del x of u prime v prime over bar plus del del y of v prime square bar plus del del z of v prime w prime bar. So this is y momentum equation for turbulent flows, time averaged y momentum equation, and this is time average z momentum equation, rho del del t of w bar plus rho u bar del del x of w bar, v bar del del y of w bar plus w bar del del z of w bar equal to minus del p bar del z plus mu grad square w bar minus rho, which came from left hand side to right hand side, del del x of u prime w prime bar, del del y of v prime w prime bar, del del z of w prime square bar. So these fluctuating components make a contribution in terms of additional stress, and we can define them as Reynolds stress, which are basically, you can see, sigma xx prime, tau xy prime, tau xz prime, again tau xy prime, tau sigma yy prime, tau yz prime, tau xz prime, tau yz prime, sigma zz prime. So these are basically minus rho u prime square bar, u prime v prime bar, u prime w prime bar, u prime v prime bar, v prime square bar, v prime w prime bar, u prime w prime bar, v prime w prime bar, and w prime square bar. This is also like a symmetric tensor. And if we add Reynolds, now this Reynolds stress tensor, we can write them as minus rho ui prime uj prime over bar, very succinct and correct representation of the components, and we can represent them by minus rho ui prime uj prime over bar. Then together with viscous stresses, we can redefine basically the shear stress and the normal stress terms. So total normal stress is this was the normal stress for laminar flow plus this component, which is minus u prime square bar. Similarly, shear stress term, this was of course for laminar flow it was mu del del y of u plus del del v of del del x of v, del u del y plus del v del x. Here it is del u bar del y plus del v bar del x and minus rho u prime v prime over bar. Here also it is minus, this will be p prime, p bar, sorry, small mistake. This will be p bar plus twice mu del del x of u bar minus rho u prime square bar. Now, so averaged equations can be written in tensor notation as del del t of u I bar plus u j, again a bar is missing, this will be u j bar into del del x j of u I bar equal to minus 1 by rho del del xi of p bar del del xj of nu, this is viscous stress component, u I prime divided by del xj, del del xj of u I bar, sorry, not u I prime, nu del del xj of u I bar minus u I prime u j prime over bar. So this was the original viscous component, which can be written as del del xj equal to nu del del xj u I bar, and then this contribution of fluctuating components u I prime u j prime over bar. And if we write term by term expression, we will get this expression. Basically, this x momentum equation, y momentum equation and z momentum equation for turbulent flow after time averaging, they can be written in this, basically in this form, which is basically written using tensor notation. If we expand I equal to 1, 2, 3, j equal to 1, 2, 3, we will get all the respective components for x, y and z momentum equation. And continuity equation is del xi operated over u I bar. Here also I equal to 1, 2, 3, if we substitute, we will get del del x of u bar plus del del y of v bar plus del del z of w bar equal to 0. So this is time averaged continuity equation. Now we have more unknowns than number of available equations. The modified system of equations cannot be closed within itself unless empirical relations are supplied from experiments to correlate the fluctuating components with the mean motion. And this is called closure problem. This may sound little complex to you, but let me explain Just consider laminar flow equations. They are the x momentum equation, y momentum equation, z momentum equation, and continuity equation. What are the unknowns? U, V, W, and P. And equations, you have x momentum, y momentum, z momentum, and continuity. 4 equations, 4 unknowns. System is perfectly well defined. Now here you have unknowns U average, V average, W average, P average. And additionally, you have basically U prime square bar, U prime into V prime bar, U prime into W prime bar, V prime square bar, V prime into W prime bar, and W prime square bar. So 1, 2, 3, 4, 5, 6 more unknowns. These are symmetric terms. So really not 9 more unknowns. It is 6 more unknowns. So 4 plus 6, 10 unknowns. And again, equations are mean equations in x, y, and z direction and mean continuity equation. So 4 equations. That is why it is being said that this problem cannot be closed now. In order to close that, you have to do something so that these fluctuating components can be expressed in terms of velocity gradients. That means, del u bar del x, del u bar del y, del v bar del x, del v bar del y, and so on, which are basically stress components. So these fluctuating components have to be expressed in terms of time averaged velocity components to basically close the system. And that is why turbulence, this is the closure problem. Turbulence stresses need to be determined with the aid of a turbulence model. Here, only models for turbulent motions are discussed. So, we have not yet introduced subgrid scale, etc. So, this becomes irrelevant. This is for the turbulent motions. And then we can say ui prime into uj prime over bar with a negative sign equal to nu t del x of ui bar plus del xi of uj bar. So del ui bar del xj plus del uj bar del xi. Del xj operated over ui bar, del xi operated over uj bar. And this is the stress component. But we are writing additionally minus 2/3 k. This k is kinetic energy, and delta ij, this delta ij is Kronecker delta. The term nu t is the turbulent viscosity, which is not known now, but it can be expressed in this way. So, if turbulent viscosity can be estimated, the term involving the Kronecker delta in this equation is so far unfamiliar. So, it is necessary to make explanation for this, and K also the kinetic energy. Now, if we, as we said or proposed earlier, fluctuating components can be expressed in terms of stress components, and those stress components are defined as turbulent viscosity multiplied by strain rate tensors, and here all the velocity components are average velocity components. Now, from this first part, we can get u prime when I and j are same. That means u prime square bar is twice nu t del x of u bar. Similarly, there is no problem when we are writing u prime v prime bar or u prime w prime bar, but again we are will end up with a special situation if we write I equal to j equal to 2, that means it is v prime square bar, we'll get again minus 2 nu t del y of v bar. Again, when I equal to j equal to 3, for example, we'll get w prime square bar, and this w prime square bar will be minus twice nu t del z of w bar. Now, apparently there is no problem, but if we add up these three quantities, we'll see sum is 0, because that will be minus twice nu t into del x of u bar plus del y of v bar plus del z of w bar, and that is continuity equation. So sum is 0 because of the continuity equation. However, all normal stresses are by definition positive quantities, and their sum, turbulent normal stresses, their sum is twice the kinetic energy K of the fluctuating motion. Now, kinetic energy K of the fluctuating motion can be defined as half u prime square bar plus v prime square bar plus w prime square bar. Now we can see why the second part was included. Inclusion of the second part of the eddy viscosity expression assures that the sum of three normal stresses is equal to twice K. If K is this, then sum of these three normal stresses has to be twice K. And that is what is done by adding this with the general expression for Reynolds stress. The normal stresses act like pressure forces, that is perpendicular to the faces of a control volume, and because like the pressure itself, the kinetic energy K is a scalar quantity, the second part constitutes like a pressure. Therefore, when this equation is used for eliminating u prime, ui prime, uj prime over bar in the momentum equation, and this second part can be absorbed by the pressure gradient, term, so that effect of static pressure is replaced as unknown quantity, and we can write that as P bar we can write that as P bar plus 2/3 K. And we can, after having added that, we can say this is the pressure now. Therefore, the appearance of K in this particular equation does not necessitate determination of K. It is the distribution of the eddy viscosity, only that has to be determined. Here, it may be also mentioned, so basically the Reynolds stress terms we can express this way, which will be basically these terms will contribute strain rate tensors. After multiplying with nu T, they will be contributing to normal and tangential Reynolds stress components, and this term will contribute to the normal Reynolds stress component but will be absorbed in the pressure term. That means modified equation for Reynolds average, modified Reynolds average Navier-Stokes equations. This will be absorbed in pressure. So separately, K need not be determined while solving the equation. However, here it may be mentioned that K can be linked to intensity of turbulence, and intensity of turbulence in a flow field has to be defined, and this is usually recommended based on experimental observation, and this is basically intensity is root over 1/3, that means mean of u prime square bar plus v prime square bar plus w prime square bar. So root over that divided by u infinity, that is the free stream velocity. So this is basically definition of turbulent intensity, and this is basically definition of turbulent kinetic energy. As such, we can from comparing these two, we can see that K by u infinity square is 1.5 I square. That can be found out, right? So I is the turbulent intensity. Definition is root over 1/3 or root over average of u prime square bar, v prime square bar, w prime square bar, entire quantity under root divided by u infinity. That is the turbulent intensity. Now we will look at Reynolds average form of energy equation. So energy equation, if we write as del T, this T is time of temperature, U del T del X plus V del T del Y plus W del T del Z equal to alpha del 2T del X2 del 2T del Y2 plus del 2T del Z2. And we apply Reynolds decomposition. U is U bar plus U prime. V is V bar plus V prime. W is W bar plus W prime. And T is time average temperature plus fluctuating component of temperature. This is instantaneous temperature. And then just what we did for the momentum equation, we substitute T by T bar plus T prime. We write conservative form of convective terms. Then substitute u by u bar plus u prime, t by t bar plus t prime, v by v bar plus v prime, w by w bar plus w prime, and t by t bar plus t prime, and apply over bar and operate following the laws of statistics. So, and if we think that the mean temperature value is not a function of time, that means steady state, we can drop the contribution of this component and we can write u bar del del x of t bar plus v bar del del y of t bar plus w bar del del z of t bar. And the terms like del del x of u prime t prime over bar, del del y of v prime t prime over bar, del del z of w prime t prime over bar are transferred to the right hand side. And if the right hand side is reorganized, then we can write del del x of alpha del del x of t bar. So this is del 2 del x2 of t written this way, del del x of alpha del t bar del x, and from left hand side we have brought this term to the right hand side, which was del del x of u prime t prime over bar. So this is del del x of minus u prime t prime over bar. Same with del del y of alpha del t bar del y minus v prime t prime over bar, from left hand side comes to right hand side. So del del y of minus v prime t prime over bar. Similarly, del del z of alpha del t bar del z minus w prime t prime over bar. Now u prime t prime over bar, v prime t prime over bar, and w prime t prime over bar, they cause additional heat flux in the x, y and z direction due to turbulent mixing, due to the turbulent motion. The total heat flux in three directions, now we can write qx double bar equal to minus rho Cp alpha del t bar del x minus u prime t prime over bar, qy double prime, heat flux in the y direction is minus rho Cp into alpha del t bar del y minus v prime t prime over bar, and qz double prime equal to minus rho Cp alpha del del z of t bar minus w prime t prime over bar. So this minus w prime t prime over bar multiplied with minus rho Cp, that is the additional contribution of the heat flux in z direction. Similarly, v prime t prime over bar with rho Cp, when it is multiplied, that is the additional contribution in the y direction heat flux, and rho Cp multiplied by u prime t prime over bar, that is additional contribution in the x direction heat flux. As in the case of turbulent transport of momentum, it is convenient to define eddy viscosity or turbulent viscosity, we have already done that, to study the turbulent transport of thermal energy. A term is introduced here, which is turbulent thermal diffusivity, alpha T. Physical diffusivity is alpha, which is a property, and this is not a property of the fluid, but property of the flow due to mixing. It's called alpha T. turbulent thermal diffusivity. The total heat flux in x, y and z directions now therefore can be redefined as Qx double prime by rho Cp equal to minus, if this is expressed in terms of eddy diffusivity and the gradient, then we can write minus alpha plus alpha t. Alpha t is eddy diffusivity, alpha is thermal diffusivity, which is a property, into del del x of t bar, q y double prime by rho Cp equal to minus alpha plus alpha t del del y of t bar, and qz double prime by rho Cp equal to minus alpha plus alpha t into del del z of t bar. So these are now expressed in terms of temperature gradients, and the entire temperature gradient. And now we have little discussion about alpha t. Like eddy viscosity, alpha t is not a fluid property but depends on the state of turbulence. In fact, the Reynolds analogy between heat and momentum transport suggests alpha t equal to nu t, what we obtain for closing the momentum equation, eddy viscosity, divided by sigma t. The denominator sigma t is called turbulent Prandtl number. So when we determine or find out nu t to close the momentum equation, that same nu t, if it is divided by sigma t, which is Prandtl number, will get alpha t, which is turbulent or turbulent diffusivity or eddy diffusivity. Experiments have shown sigma t, that is turbulent Prandtl number, varies very little across the flow. Many models make use of sigma t, that is turbulent Prandtl number, as a constant. For the flow of air, a value of 0.9 may be chosen. So our task will be to find out correctly nu t. We'll use that for closing momentum equation. Then we'll divide the same value by sigma t. Sigma t is turbulent Prandtl number and it is constant for a flow. For example, for air we can take 0.9, and then we'll have alpha t. We'll find out alpha t. Once alpha t is known, we'll be able to close this equation, which is basically time averaged energy equation. U bar into del del x of t bar, V bar into del del y of t bar, W bar into del del z of t bar. So U bar dt bar dx, V bar dt bar dy, W bar dt bar dz equal to del del x of alpha plus alpha t. This alpha is physical property, thermophysical property, thermal diffusivity, plus alpha t, which is basically due to turbulent mixing, into del t bar del x, plus del del y into alpha plus alpha t dt bar dy, plus del del z of alpha plus alpha t into dt bar del t bar del z. So this is time averaged energy equation, which has to be solved together with time averaged momentum equations. Time averaged momentum equations will give us velocity components. We'll plug in those velocity components and then we can solve the energy equation for determining temperature. But while closing the momentum equation, As I said, determining nu T is a challenge, is a sort of involved task. There are simple models, there are complex models. In order to reach a more accurate simulation, you must have heard about K epsilon model, you must have heard about large eddy simulation technique, you must have heard about DNS, direct numerical simulation technique. So if time permits, we'll take up briefly those discussions. But nu T has to be determined or estimated. Then momentum equations can be closed. And after nu T, having known nu T, if we know turbulent Prandtl number for a particular fluid, like for air it is 0.9, then we can find out alpha T, which is thermal diffusivity, turbulent thermal diffusivity, turbulent diffusivity, and together with thermal diffusivity we can apply that to energy equation and solve for temperature. Thank you very much. Thank you for your interest.